Welcome to the ESNT, or Electronic Security Networking Technician, webinar training section number 1. The ESNT training, or Electronic Security Networking Technician training, is a certification program that is administered by the ETA, the Electronic Technicians Association. This is a certification, a training, and testing program for physical security technicians and personnel to learn how to accurately and safely and properly program and install IP-enabled physical security devices such as CCTV cameras, NVRs, DVRs, access control panels, etc. onto customers' networks. This is a complete and thorough training program. The webinar section of this is basically the lecture portion of our training. To receive your ESNT certification, you must finish the webinar series and then attend a one-day hands-on networking lab where we do hands-on work with computers, cameras, etc., network switches and equipment, show you how to work the things you will learn in these webinars, and also that is where your certification test is administered. You can check our website, www.slaytonsolutionsLTD.com, for its certification class and testing dates in your geographic area. This is the first section of the webinar series, and it has to do with general networking concepts. My name is Dave Ingebrigtsen, and I'll be your instructor today. I've been in the electronic security business for 33 years. I am ESNT certified as well as fiber optic certified and Network Plus certified. My company, Slayton Solutions, provides vendor-independent training programs for our industry, for technicians and salespeople in IP and fiber optics. So let's get started with our first webinar presentation. We are going to be talking about all the aspects of networking in these webinars. We need to understand what's called the topography of the networks. The two basic kinds of networks we will discuss are LANs and WANs. First thing we'll talk about is the LAN, the local area network, as you see illustrated on the screen. On the right-hand side, we have the client PCs. These would be the workers in their cubicles or offices with their laptops or desktops. Those devices are connected into the network switch, and there can be multiple switches. We will discuss that as well. And on the left-hand side, we have the network servers. These are the devices that store and provide files, applications, and information. Now, one thing I want you to notice in the typical modern, and that's what we're seeing here, is the modern LAN topology, is that every device is connected to only one other device. On the back of your computer or on the side of your laptop, there's only one RJ45 socket. So one cable is connected into your computer, and that is plugged into something else on one other thing on the network. In most cases, this is going to be the network switch. So every device on the network is on its own cabling, and this is important to understand about the modern network. Now, the second type of network that we are going to discuss in great detail in this training series is the wide area network, or WAN. And the biggest of wide area networks is, of course, the Internet, where there are tens of millions of local networks, just like the network that you've got in your house and the network I have in my house. They're connected to the Internet through our DSL, cable modem, satellite, however they're connected. So conceivably, and if we wish, we can make it so that these various local networks can communicate with each other. When we've got a wide area network, that is it is two or more local networks that have the ability to communicate with each other. It could be within a single building, or it could be as big as the Internet, but that's what a wide area network is. Our local area network is typically kept under one roof. You've got probably one network in your house. That's what is most common. So you can think of a local area network as generally within one building, where our wide area network is going to cover multiple locations. To understand networking, we have to talk about some very basic items, and the first one is the protocol. The protocol is the language that the machines speak to each other. And just as we have a protocol when you answer the phone, when my phone rings, I pick it up and I say, Dave Ingebrigtsen, can I help you? We've got a way that we talk and a way that we communicate. And we've got languages like French and English and Greek and Russian. And if we want two machines to talk to each other, they have to talk the same language. Just like if two people want to talk to each other, they have to speak the same language. And those languages are called protocols. Now, the protocol that is most commonly used in cabled networks, and I say cabled because you'll find out as we go through this that we can connect devices onto networks with UTP, unshielded twisted pair, with coaxial cable, with AC power line, and also with fiber optics. But when we talk about a cabled network, we generally talk about Ethernet. And the Ethernet protocol, it's a language that the machines speak. The Ethernet protocol was standardized by an organization called the IEEE, the Institute for Electronic and Electrical Engineers. They established the original standard in 1985, and it was called 802.3. And what this standard provided for, and we're going to get into the details of all these things, the topology, the media, the speed, and the access method, but it provided a standard of a language so that various manufacturers could build products to the standard. What's important about these IEEE standards for you to grasp at this point is that they are free. You don't have to have a license to put Ethernet into a product. Anybody can build Ethernet products. The IEEE provides the information at no charge, and there's no licensing fee involved. So let's talk about the original Ethernet standard. 802.3, the topology was a bus or a star. And we're going to talk about what a bus topology is in a little bit later, but basically that means in our original Ethernet, if we're putting in a system in 1987, that cabling was a single coaxial cable, typically a coax, that ran all around the building, and every device was hooked up to that same piece of copper. Now, the access method was called carrier sense multiple access collision detection. We're going to talk about those access methods and what they mean a little bit later, but it's an important thing to remember that it's what we call a contention or contentious media or access method that is used. Now, the bandwidth of the original Ethernet, or speed, was 10 megabits per second, or 10 million bits per second. A bit is a single one or zero. All network communications is in ones and zeros. And so 10 megabits, 10 million bits per second. And it could be half or full duplex. So it could either be a call and response type of system on a single cable, or it could be a full duplex communication if it was on something where there was multiple cables, so that you could have two basic lanes of traffic that it could travel to be on full duplex. Obviously, if it's hooked up to one copper cable, like some of the original Ethernet networks were, devices can only speak half duplex. They'd have to talk, and then they'd have to wait for the response to come back on the same wire. So here you see 802.3, the way it was originally deployed back in the 80s and into the early 90s. And what was most common is what you see in the upper left-hand side, where we had that single copper cable, and then we had taps coming off of it that would connect up our computers, our servers, our printers, and other devices. An interesting thing to note is that Ethernet was originally conceived to share the printers. Old-time printers used to be very big and very expensive. They took a lot of floor space. And people found out when they put computers into their networks, or when they put computers on people's desktops, everybody's got to be able to print out what they're doing. So we've got to have printers, and we don't have them. In the old days, we didn't have the money to put a printer on everybody's desk. We wanted to share the printer. So that is where Ethernet, the idea of Ethernet happened to the people who originally conceived of it. And nowadays, of course, we can share printers, we can share internet connections, we can share video, we can share audio, we can share files and applications, all this stuff we can share on networks. But let's get back into our original 802.3 and take a look at what we've got here. Basically, as I stated, most of the time is what you saw on the upper left. A little later on, they developed products or devices called hubs, and what a hub does is when a data packet enters it, the hub retransmits it to everything that's connected to it. So a hub basically replaced that one cable with a box that hooked everything together, and you see illustrations of this on the screen. But one of the key issues and one of the key problems with this first deployment of Ethernet was, if you look at the upper left-hand side and think about it for a minute, you realize that if everything's connected to the same piece of copper, then only one device can talk at a time. And as our networks get more complex and more users get on the network, hey, more than one device is going to want to talk. And when more than one device wants to talk, remember that our method of access to the network is a contentious method. There's going to be data collisions, and we're going to have to deal with those. And we're going to talk about those in this section of the training. Now, 10 years later, they realized that they could make Ethernet faster, so they came up with the 802.3U standard. Now, this is the single most common standard that is in use today. Virtually everything that you would buy not in the year 2011, everything you buy is going to do at least 100 megabit or fast Ethernet. Notice that its access method is still carrier sense multiple access collision detection. The media could be a twisted pair or fiber optics. And if it is twisted pair, like Cat5e cable or Cat6, Cat7, it's going to use 2 of the 4 pairs that are commonly in one of those cables. 1 pair to transmit and 1 pair to receive. The maximum bandwidth or speed is 100 megabits per second, and we explained that before. And this is typically a full duplex communication. Now, there are some other standards that relate to gigabit Ethernet, and this is 1,000 megabits per second or 1 gigabit. So we've got different standards here based on what the media is. Is it fiber optics? Is it twisted pair? Is it single mode fiber optics? So we've got these 3 standards, 802.3Z, 802.3AB, 802.3AH. Now, one thing for you to remember is that the most common type of cabling used for Ethernet is the twisted pair cable, the Cat5e cable. If we are doing or transmitting gigabit Ethernet on a Cat5e, a standard Cat5e cable, all 4 pairs are used, where in our 802.3U, our 100 megabit, we're only using 2 pairs. In our gigabit Ethernet, we're going to use all 4 pairs of the Cat5e cable or Cat6, Cat7 to transmit and receive the data. Now, there's also a standard, the 802.3AE, which is 10 gigabit Ethernet. Now, 10 gigabit Ethernet is commonly used for communications between telecom closets. We've got a network switch in telecom closet 1, network switch in telecom closet 2, and we have what's called the backbone cabling, which we'll discuss in more detail later. But there's cables that connect these 2 telecom closets. Typically, as you see mentioned here, they're going to be single mode or multi-mode fiber if they want to do 10 gigabit Ethernet. So they're going to put a big pipe between the 2 telecom closets because there's going to be a lot of data traffic between them. So that's going to be on fiber optics, and it's the 802.3AE standard, and it came out in 2002. Just so that you know, they are also working on 40 gigabit and 100 gigabit Ethernet standards, which we will likely see possibly in the near future, but understand that it takes the IEEE a long time to actually ratify a standard. Now, here's a summary of our standards. The ones that are important to us as physical security technicians are the fast Ethernet and the gigabit Ethernet standards. All of our cameras and devices that we're going to buy, NVRs, DVRs, are typically going to be 100 megabit devices if it's a camera, if it's a video encoder. And 100 megabit works just fine for most of our applications. Even a megapixel IP camera that's putting out 10 megabits per second. Can 10 megabits per second of video pass through a 100 megabit per second link? Certainly it can. So we've got plenty of room there to connect that camera up to the network switch. Where the gigabit Ethernet comes in for us is for when we're thinking about where we're going to store recorded video. We might have a network attached storage or some other method by which to store it, some other device with hard drives in it, and that, if we have a number of cameras coming to that, that may have to be gigabit Ethernet in order to have enough bandwidth capacity to bring in 10, 15, or 50 cameras that we want to record onto that onto the hard drives that are in that device. So fast Ethernet and gigabit Ethernet are the ones that we're concerned about primarily in our industry. Now here you see the wireless standards. The IEEE also sets the standards for Wi-Fi wireless, which is wireless Ethernet. It's Ethernet's wireless brother. It addresses the same, it programs the same, but it's wireless. The cable that would, or the media that runs between two devices has been replaced with radio frequency transceivers. And here you see the Wi-Fi standards from 802.11a down to 802.11n. Understand that the most popular wireless standards in use today are the 802.11g, which is 54 megabits per second maximum bandwidth, and the 802, and what's coming on strong is the 802.11n with 600 megabits of maximum bandwidth. And you can see, I think you can see, what is going to come in the future is more and more of our customers at the enterprise level, as they are considering recabling their buildings, they are going to go more towards the wireless devices, because cabling is expensive. Cabling is expensive to install, expensive to maintain. It's hard to do moves, adds, and changes, and it's easy to do with wireless. Many of you probably have Wi-Fi in your own homes, in your own businesses. You understand the beauty of it. Well, now there's big bandwidth Wi-Fi. And there's some details on the bottom of the slide here that talk about OFDM, or orthogonal frequency division multiplexing, and direct sequence spread spectrum. These are just terms that are used to explain how to standardize how the transmitters and receivers use the frequencies that are available to be able to transmit the data that they do. Now, what makes the 802.11n standard different is that it uses what's called MIMO, multiple input, multiple output. So your 802.11 access point, 802.11n access point, has up to 4 antennas on it. And when it is communicating, it can use up to 4 frequencies simultaneously to transmit and receive. So that's how, it's one of the ways that it achieves the big bandwidth that you see listed here on the screen. Now understand that when we talk about Wi-Fi and bandwidth and distance, the further we get from the access point, from the antennas of the access point, the less bandwidth we're going to get. Also understand that these bandwidths that are listed here are per the access point. If you have an 802.11g access point built into your Wi-Fi router like I have at my house, it's supposed to deliver 54 megabits per second, and indeed it does. But it's 54 megabits for everything that's connected to it simultaneously. So if there are 6 users that are hooked up to, that are communicating with the same access point, they don't each get 54 megabits. They share the 54 megabits. And it's the same with all the other Wi-Fi standards. So it's shared bandwidth. It's not per user bandwidth. I want to make that clear to you. So our bandwidth can be reduced by distance. The farther we are from the access point, the attenuation is going to lessen our bandwidth capability. There are some directional antennas and things you can do to extend or to limit the coverage area of Wi-Fi, and we're going to cover that in some detail in a later section of this training. But what I want you to see here is this chart. It shows us what happens to the bandwidth as we move from left to right on the bottom axis. As we move away from the access point, we lose bandwidth. You see the 802.11b stays pretty strong at 11 megabits per second until it gets to about 170, 175 feet from the access point, and then it starts dropping down. Notice how the 802.11g starts off really big, 54 megabits per second, But then as we go further distance, if it's at 175 feet from the access point, guess what? It's at virtually the same bandwidth level as the 802.11b device. So what does this mean to us? The further away we are, the less bandwidth we have. Also, understand that when they set these standards, this assumes, think about this slide and think about doing this on a football field where there are no metal obstructions, there's nothing to obstruct the radio signal. In the real world, and we know this from our experience with alarm equipment, in the real world, we are not going to get the maximum distances that any of the manufacturers discuss with their products. It's just not there. There's going to be steel file cabinets. There's going to be metal lath in the walls. There's going to be foil-backed wallpaper or insulation. There's going to be something that's going to attenuate the signal and make it so we don't get these maximum distances. I certainly would not be comfortable saying I'm going to install a Wi-Fi IP camera that's 150 or 200 feet from the access point and expect it to work properly, because it probably isn't going to. There's going to be something that attenuates between that device and the access point antenna. Now, whether it's Wi-Fi or it's wired Ethernet, we have to consider the concept of the collision domain. When the original Ethernet was formulated, by the way, this slide you see on the screen, the drawing is from a gentleman named Bob Metcalf, who was really the key person who invented Ethernet back in the late 70s and into the early 80s. His original idea was he would have these transceivers, as you see them drawn, hooked up to what he called the ether, and the ether turned out to be, in most cases, coaxial cable. Now, if we've got all those devices hooked up to that one piece of copper, how many devices can talk at one time? Only one can. And because Ethernet is a contentious access medium, devices are going to end up colliding. When they try to transmit, they're going to step on each other, and those are called collisions. And if we have collisions, it's going to cause retransmission of the data, and it's going to slow down our network. So we know that the data packets can collide based on how the network is cabled. Notice on the slide here that when we moved from the hub to the network switch, which is the common device that is used today to connect devices up onto a network, our switch really eliminates collisions. But let's explain what happens with the collisions and these access methods and how they work. We know that we can have collisions, and the IEEE standards dictate how these collisions are going to be handled when they do happen. Now, our two network access methods are carrier sense multiple access collision detection and carrier sense multiple access collision avoidance. Wired Ethernet uses the first one, collision detection. Wireless Ethernet or Wi-Fi uses collision avoidance. And both of these access methods are considered contention or contentious methods. Now, carrier sense multiple access collision detection is in the 802.3 standard and as they move forward. And what this does is if a device is transmitting and it hears another device stepping on its signal, both devices will send out a jam message because they'll both hear they're getting stepped on. They will wait a random number of milliseconds and then they will retransmit their signal. What this does is the more data that we try to push through the network and the more users we have on the network, the more collisions we're going to have. And the more collisions we have, the more retransmits we're going to have. And the more retransmits we're going to have, the more collisions we're going to have. So it becomes kind of a bad, endless loop that slows down our network. And this is what happened in the old days when the network, our Ethernet networks, were all connected through hubs or connected on a single coaxial cable. This doesn't happen nowadays. Our network switch takes care of the collisions in most cases. But here you see what the old days look like, and what is in the red circles are our collision domains. This is how many devices can collide with each other. In the old days, when they were designing networks, one of the key design elements was how big will the collision domain be when devices start to collide. The more devices on that single coaxial cable, the more collisions we are going to have. Now, in wireless Wi-Fi, we've also got a collision handling mechanism. It's called collision avoidance, carrier sense multiple access collision avoidance. Now, what happens here is a little bit different. Your Wi-Fi radio in your laptop or in a wireless camera is constantly listening to the frequency that it is programmed to. And when it needs to transmit something, it's going to listen to the frequency and see if the frequency is idle. Nobody else is talking right now. If nothing is communicating, then the device will communicate. If it listens and it hears other devices communicating, it will wait a random number of milliseconds, then try to listen again. If it hears a clear channel, then, it is going to do its transmission. Now, one last thing we're going to talk about here in Section 1 are protocol models. There are thousands of manufacturers of hardware and software for networks. We could start naming them. I mean, they're Dell and they're Cisco and they're Honeywell and they're Panasonic and they're Bosch and all our vendors and Axis and everybody else. They're building network devices. And one of the goals of networking, and you'll see this when you attend our one-day hands-on training program and certification testing lab, we'll have devices from 9 or 11 different manufacturers all hooked up, and they all will work together. That's because all the manufacturers follow what we're going to talk about now, which are these protocol models. And the first one is called the Open Systems Interconnect. Now, I want you to understand that the OSI protocol model and the next one, these are concepts. These are ideas. They're not a brick and mortar thing. They are ways that the manufacturers of hardware and software, ways they look at their products and how they're going to interact with each other so that different manufacturers' products can work together, hardware and software. Now, there are 7 layers in the OSI protocol model: physical, data link, network, transport, session, presentation, and application. What we're concerned about as technicians when we later on, when we get into the IP and MAC addressing of devices, is the first 4 layers, 1 through 4. Our segment, our packet, our frame, and our bits. These are the part of the OSI protocol model that we should remember, because these are the things that we're going to be working with when we put in our IP addresses, when we put in our software ports. Our software ports are in layer 4. Our IP addresses are in layer 3. Our MAC addresses are in layer 2. And our data bits are going to be transmitted and received on layer 1, or the physical layer. Now, an easier way to look at this is another concept that's more commonly used, called the TCP/IP protocol stack. It looks very similar to the OSI protocol stack, except it only has 5 layers, so it's a little easier to deal with. We've got layer 5, which is that application layer, and then layers 4, 3, 2, and 1 are the same as the layers in the OSI protocol stack. And again, in layer 4, we're going to have our software ports. In layer 3, we're going to have our IP addressing. In layer 2, we're going to have our MAC addressing, and our data bits are going to flow out and flow in on layer 1, which is the physical layer. Now, this is the end of the first section of this webinar series. This is the ESNT training program. This presentation is provided to you by Slayton Solutions Ltd. If you are interested, there are training manuals that have been approved by the ETA that you can buy at our website. There's a Technician's Guide to Networking for Security Systems, and there's the Technician's Guide to Networking for Security Systems Enterprise Solutions. Both of these books are available at ADI, and they're also available at my website, our website, www.slaytonsolutionsltd.com. Now, you also at our website can purchase the ESNT study guide. With the study guide, it's going to be a disc which is going to include a PDF of all the webinar sections, so you can print them out if you like. The recorded webinars will be on it, and there will be a quiz with answers for each section of this webinar series. So if you get the ESNT study guide, then you've got a way that you can test your own knowledge to make sure that you gathered and you understand the information, and you can go over the webinar again if you like, so that you get what you need to know from each individual section. And you can secure your future with the ESNT training and certification program as presented by Slayton Solutions. I thank you for watching this webinar, and we will be moving on to Section 2.